Yeah, okay. Yeah, what's your question?
So like for the D4K prime, right? Isn't there the negative factor
Oh, you mean
when
this
you're
one?
switching? Yeah.
Uh, Let me see. So, okay, so you're saying D4K and e to the ikx over here, phi star of k, right? So if I write k prime, if I do a change in variables, k prime equals to minus k, so that, um, oh, so you're saying this should be d4 minus k prime. Is that right?
Yeah.
Uh, um, mm, yeah, I think, yeah, I think it's typo. Wait, let me just check. Let me just cross check with, uh, let me just cross check with some, because I'm seeing if the condition for real fields is condition for real fields. Let me. Yeah, I think you're right. Let me just double check on that. Uh, okay. So how would that edit the equations? That would change. That would mean that this is has a negative sign associated with it, right? And and that would imply that, yeah. So that would change the condition of having real fields to this picking up a minus sign. Uh, that seems right. My concern right now is I haven't seen such an equation around before, so uh I just want to double check. Maybe yeah, let me just double check on that. Or maybe I'll check it after the class and um yeah, okay, can I get back to wait, hold on. Oh, I noticed something. It's probably because okay, it's probably because you change the limits of integration as well. So yeah, okay. So previously you integrate from minus infinity to infinity for each k, right? And then after you change it to k prime goes to minus k. Yeah, okay, that makes sense. That makes a lot of sense. So it becomes minus k prime x phi star minus k, correct?
Yeah, I see that. Yeah.
Minus k prime. And then you change the limits of integration from you basically flip it around. So that's why eventually the minus signs it become minus infinity to infinity for d4k prime. Yeah. Yeah, I hope that answers your question. Yeah.
Yeah, okay,
Thanks for
thanks.
pointing
Yeah.
that out. I think I should make my slides clearer. I should insert a case for why. So this will be on my to-do. I'll make it clearer. Yeah. Thanks for pointing that out. Yeah. Cause I think I remember this condition being kind of true. So I was a bit taken aback when I realized that it might be wrong. Yeah. Okay. Okay, great. So where were we? We just finished talking about yes, we just finished talking about the classical field theory, expanding phi in terms of d4k, right? And narrowing it down to d3k using the on-shell condition. So okay, I'll leave the quantum harmonic oscillator to another time. Today I want to spend the remaining time talking about the three quantum mechanical pictures. Okay, so this is if you have experience with some quantum mechanics, one will know that in quantum mechanics, the way we often learn in undergraduate is we start off with a wave function phi. Okay, so the usual pathway is we start off with a wave function phi. We usually learn that it's a function of space-time. Oh, no, sorry, a function of, yeah, space-time, sorry, space-time. And how it evolves in time, right? Time evolution the is governed by the Hamiltonian. So uh minus I over h bar h of phi of x, right? Where this Hamiltonian is a differential operator. And usually the Hamiltonian is usually a Hamiltonian is it's just the parameter, the differential operator representing the energy of a function. And this way we say that the Hamiltonian generates time translations. And you see this lingo being thrown around a lot more. Like for example, rotations generate the angular momentum generate rotation. So we eventually see that you might also hear that angular momentum, right? J generates rotations. And then you also hear that momentum generates translations, and likewise translations generate momentum. And this is all related to the Lie algebra, which I've put some resources in the previous lesson. So this is all related, made rigorous using Lie algebra, right? You see that generators are actually elements of the Lie algebra. So it's all made rigorous in that sense. And these rotations and translations, they are symmetry groups. So groups symmetry groups of the of the of the Hilbert space. Specifically, the Hilbert space is going to be a representation of these Lie groups. But anyway, that was a short digression. But this usually we learn the Schrodinger equation, and then we learn that that's the way quantum mechanics works. But here's a bit of a paradigm shift. Actually, when we besides the Schrodinger, besides the Schrodinger picture, we actually there was actually a parallel development. There was actually a parallel development of quantum mechanics known as Heisenberg's matrix mechanics. So Heisenberg matrix mechanics, and basically, roughly speaking, without going into too much detail, Heisenberg's matrix mechanics was it involved calculations of matrices. So as an example, right? Um, um, in the Schrodinger picture, when you have a raising and lowering operator, we 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 think of it as acting on the states, that right, the quantum states. But in Heisenberg matrix mechanics, we we think of the information of the quantum system, right? Instead of being encoded in the states, being encoded in states, they're actually encoded in the operators. In the operators, for example, the momentum operator or the translation operator. And then these operators are the ones that using things like commutation relations, they are the ones that we actually need to do computations on. So some of these operators may be matrices, right? For example, in the case of the spin half system, there are 2 by 2 matrices. In cases, they could be differential. Basically, the Schrodinger picture mainly told us that the Schrodinger picture basically told us that quantum information is stored in states, right? It's stored in the states. Whereas Heisenberg's picture basically told us the quantum information was stored in the operators. It's stored in operators, right? And why it's called matrix mechanics is because operators, in some basis, can be represented as matrices, even if they might be infinite dimensional matrices. So, which one is the more correct one? The answer is actually both of them are equally valid viewpoints. And in today's lingo, we actually call them different pictures of quantum mechanics. So I don't think I've gone through this yet, right? Yeah, just stop me if I have. I do not want to risk repeating myself. Yeah. So the upshot is that quantum mechanics, what actually do we calculate in quantum mechanics? The answer actually in quantum mechanics, we calculate expectation values. Expectation values they are similar to what you hear in statistics, right? In statistics, we hear that expectation values, EV, if you play professional poker, right, you hear that professional poker players, they want to always take actions that increase their expectation value. So that expectation value uh is a statistical expectation value of some quantity, right? It's basically across all states, right? Across all states, sorry, maybe not states, across all across all possible scenarios, we sum up the value of that expect. So let's say we want to find the expected value of let's say some quantity. I just call it A. So I sum across all scenarios, right? The probability of that scenario and the value of A in that scenario, right? So expectation values, they are purely probabilistic, right? They are sum over the probabilities, weighted by the probabilities. They are a weighted sum over the probabilities, and they tell us basically the average. If you repeat the same experiment multiple times, many times, it eventually converge to this expectation value. And in fact, we even have a theorem that tells us, it's called Ehrenfest's theorem. It tells us that expectation values basically, yeah, so if we calculate the expectation value of position, right, and take the time derivative, it equals momentum. So Ehrenfest's theorem basically tells us that quantum mechanics, yes, you have uncertainties and all that, but if you calculate the expectation values, the average, right, you actually recover classical mechanics. So essentially, quantum mechanics is all about expectation values of operators. In this case, there could be operators about, yeah, all the Hermitian operators that we have. There are things that we want to calculate. So why do we so this is why we want to calculate them, because they tell us we can extract information from them, right? But how do we calculate them? We say the expectation value of a state, uh of an operator, sorry, expectation value is always of an operator in the state psi, right? It's given by the bracket notation like this. And this is basically if we think of the state psi as a column vector, then, if we think of the state psi as a column vector in the cat, right? Then the bra in bracket notation, this is under Dirac's bracket notation, the bra would then be a row vector, right? The Hermitian conjugate, to be specific. And if we think of the operator A, right? A as taking a state, a state, right? And mapping it to another state, mapping to another state A of psi, then we can think of A as a matrix that brings us from one column vector to another column vector. And so this is actually essentially is a multiplication of so this expectation value, right? This expectation value is is going to be a real number, right? So we have made a column vector, a row vector times a column, sorry, a row vector times a matrix times a column vector, and that gives us a single number. Could be real, could be complex. It depends on what the operator A is. So some of these operators, okay, so that's great. We now know how to calculate expectation values of operators in some state psi. But these operators could have time dependence as well. For example, if our if our Hamiltonian, which represents the energy, right? If we're talking about a spin in a spinful particle in a magnetic field B, we know that there's an energy associated, right? There's an energy associated with uh with a spin in the magnetic field, right? The spin wants to align to the magnetic field. So the energy is proportional. This is supposed to be H. Energy proportional to that. Um, and and because the magnetic field is something we can change experimentally in time, right? For example, you can have a rotating magnetic field if you want to do things like if you want to cause things like Rabi oscillations. Our Hamiltonian operator could in general be a function of time. So for example, if the magnetic fields are a function of time, then the Hamiltonian naturally is a function of time. Okay, so this is where, so I wrote a subscript over here, denoting subscript S, because this is basically explicit time dependence, right? The Hamiltonian depends on time, right? The Hamiltonian is a formula that explicitly has time dependence in it. And this is important to distinguish with time evolution, right? If you have tried to read the three quantum pictures by yourself, you may be often confused by the notation of H sub, you have a notation where you have some operator A subscript H, right, representing Heisenberg, and then you have some operator A subscript Schrodinger, and then you see that Schrodinger has some time, if the Schrodinger picture has some time dependence, then the Heisenberg picture, like isn't this already a function of time? Like how can we say, and it'll be very confusing if you do not notice the difference between time dependence and time evolution. That's what I mainly gained from trying to prepare these notes. So time dependence, right, is referring to in the Schrodinger picture where the operators do not evolve in time. And time and time evolution, right, is telling us how the operators will evolve in time according to the time evolution operator. So it's best shown with this graphic over here. If let's say I have a I have a Schrodinger, I have a operator A that has time dependence, right? If it has time dependence, then if I take the expectation value of that operator that has time dependence, right, with respect to a state psi, and so the state psi of t, right, the state psi, okay, maybe this is not the best way to write it because this implicitly assumes the Schrodinger picture already. So rather, right, if I have some state psi at some initial time t equals to 0 at some initial time, right, how will this state evolve after some time t, right? It evolves according to the time evolution operator, which I'll denote u. We don't know the exact form of it later at the moment, but we'll find out what it is later. So this is time evolution operator. Keyword here is evolution. And it evolves to some state that is denoted this, right? Still very abstract. We do not have any concrete expressions for it at the moment. So if we take the expectation value of that, right, we can see that expectation value of that with respect to time, right, is just this entire thing over here. And this is essentially the central equation of, in some sense, this is the central equation that governs, right, expectation values. This is the mother of all equations, right? If you're ever confused, just start from here. This should be the starting point. So from here, we can then consider different ways to interpret this mother of all equations for the expectation value. One of them is, what if we put the brackets around the u and the psi? If we do that, then we actually get that the operator, right, doesn't change, doesn't have time evolution, right? It still might have time dependence, but it doesn't evolve with the u operator, right? And where is the time evolution operator u attached to? Is attached to the state. So that tells, in the Schrodinger picture, right, which is related to Schrodinger equation, right, it tells us that the state psi is the one that evolves in time, whereas the operator doesn't evolve in time. It could still have time dependence, but it doesn't evolve with this u, right? Yeah, and then if we put the brackets around u, a, and u, right, u and the operator and the u, then we get the Heisenberg picture. And later we'll see, if we want to do the interaction picture, it involves splitting up this u operator, u, and splitting up into u naught and s, right? Where u naught is time evolution under the free Hamiltonian. We'll talk more about that later. And S is the interacting. I'll have an explicit expression for S later, but it's roughly referring to the interacting part. So this is the free part and the interacting part. And the interaction picture later tells us that the operator evolves under the free time evolution, whereas the state evolves under the interacting time evolution. So the first picture is that we bracket the u and the, so that under time evolution, right, your states evolve under time evolution. And comparing that, so this is from what we got from above, and comparing that with the equation we have, Schrodinger equation, we can deduce that we can actually try to find expression for u, because this evolves, right? And this tells us that state psi evolves also. So comparing the two pictures, we want them to match. we can we can find out expression for u. So what would that involve? Now over here, I'm gonna work in the most generality where the Hamiltonian is actually a function. It's actually as time dependence. I'm not gonna assume anything because if we get the most general result, then I argue that if we get the most general result, then we can whatever other results that we see online, we can actually take it as a special case. So yeah. Okay, so substituting the first equation into the second equation, we get this, right? Um, so this holds for any initial state psi naught, right? Because we can plug anything in psi naught, any value of psi naught into the equation. Um, this is so this is actually not an equation that cares about psi naught at all. It's actually an equation for the differential for the time evolution operator, and that gives us this thing. Okay, so how do we solve this differential equation for the time evolution operator? Uh, if we write it like that, we can actually integrate both sides with respect to t. And so if we integrate the left-hand side, we integrate the both sides with respect to t. Wait, so something to note over here is that u of t naught, sorry, u of t equals to 0, right? If there's no time evolution at all, then the state psi must not have changed, right? If you apply this on state psi naught, right, there's literally no time evolution for this state psi naught. So this must be psi naught. So this essentially u of t is equals to 0 must be the identity operator, which we sometimes write as 1 as well. Yeah, so whether it's the identity or whether it's 1, it depends on which kind of quantum system we're working in. If the quantum system we're working in is a matrix, something involving a finite something like, for example, spin, right? Then it'll be a identity matrix. If something involving, if it's a function space, then we can write it as 1. In other cases, we actually need to, it's actually um yeah, it's basically the identity of whatever space, whatever Hilbert space we're working in. So if we integrate, okay, back to this, if we integrate the equation 35 from time t equals to 0 to time t equals to t1, some point in time at the moment, uh, then we can see that the left-hand side, okay, so the I h bar is just a constant factor. Then the left-hand side becomes u of t1, right, minus u of t equals to 0, right? And the right-hand side becomes the integral of 0 to t1 h of t prime u of t prime dt prime, right? And then this u of 0 is just 1. So we bring it over to the right-hand side, we get 1 plus the constant factor, and then we get this. Okay, so this t prime, right, I label it as t2. And why do I do that? It's because now I actually have an explicit expression for t, for the time evolution operator of u of t1. But what's the problem over here? It actually depends on the same expression, right? Just that we substitute in time t2, which we integrate over from 0 to t1. So what this allows us to do is actually we can do it recursively. And now substitute this back into here, and substituting it back into there, right? Wait, I think I might have, okay, it makes sense. Sorry. So over here, I have, so substituting u of t1 back into this will give me this is just the previous term. This term, it comes from the 1, right, multiplied by this over here. Then there's other terms, right? So this is there's other terms. So this is the same. So now I substitute, this guy over here back into itself. So it becomes this double integral, right? Because I'm substituting this left hand side into this u, right? So this left hand side is the integral already. So there's one integral here, and then there'll be another integral from this, right? So it essentially becomes this, and it repeatedly happens until forever actually. And so this is known as, later known as a time ordered time ordered product use, which I'll show later. So if I simplify that down, right, I get, so this is the expression for the time evolution operator. Um, okay, so what's nice about, let me just fill in some of the steps over here. So how do I get from this to here? The idea is that if I integrate, so the idea is to draw a triangle. If I have integral of 0 to t1, right? Um, if I have 0 to t1, integral of 0 to t1, and then for each one of them, right? So the t2 is the variable that goes along it. But then I have zero integral from 0 to t2. So at this point, right, t2 equals to 0 at this point. At this point, t2 equals to t1, right? So then I have integral from 0 to t2 for each one of them. So what it looks like is, um, if I'm going to draw the second one over here, I'm going to draw the second one out, then it looks like a triangle for domain of integration. So this is the domain. This is the region of integration, essentially. This is region that I integrate over, represented pictorially. And we'll see why I want to do that later, because this expression is quite intractable, right? I want to express it in terms of something nicer later. So this is the T2. So over here, T2, this is T3 equals to T. So at every point in time, right, this is the integral along this direction is for T3. So I hope it's clear, right? You integrate from the T2 goes from 0 to T1, right? And for each one of them, for each value of T2, I integrate from T3 equals to 0 to T3 equals to T2. And as T2 increases, right? As T2 increases, then the T3 goes from 0 to 0 to 0 to some small amount, 0 to 2, 0 to 3, 0 to 4, 0 to 5, 0 to 6, all the way to 0 to T, all the way to 0 to T1. So it's, if you want to think of it in terms of coding, right, I have a for loop that brings me from T2 equals to 0 to T2 equals to T1, right? And then inside this for loop, I have another for loop that let me go from T3 equals to 0 to T3 equals to T2. And then inside, so that's for the second one. If I want to try the third one, right, I have another for loop that goes from T4 equals to 0 to T4 equals to T3. So if you try this for loop out, you realize that there's a triangle pattern to it. Yeah, I just wanted to draw this analogy with nested for loops in if you know coding. So if we draw this triangle, right, then one can realize that for every what does this triangle represent? It represents the region I integrate over. But what is this region? For every point inside this region, it corresponds to a h of T2, h of T3, and so on, right? Where T2 is always greater than T3. So what this expansion guarantees, right? I cannot commute these because they are operators, right? They are matrices. Matrices cannot be commuted. So their order must stay the same. And what do we see is that every time we have two H's, right? Tn and Tn plus 1, right? It's always guaranteed that because these are matrices, they cannot switch their order. And because of the way I expanded it in, they must stay in this order. But because of the domains of integration, the limits of integration, Tn plus 1 is always going to be less than Tn, right? In this case, T3 over here in this for loop, it only went to T2, right? So T3 is definitely less than T2. Okay, I'll try to speed it up. This is quite, yeah. Uh, okay, so T3 is always less than T2. Uh, so 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 what I can actually do is, if I don't want to integrate over a triangle, right, because it's quite unnatural, what I can do is I can actually integrate over a square. In the case of the two time dimensions, I can integrate over a square, and of course that would initially sound bad because um now I'm integrating over some extra values, right? Now previously I had this. Now if I h of T2 and T3, now I'm going to end up integrating h of T3 and t2. Wait, no, sorry. Now I'm going to end up integrating over, if I expand the region of integration, then now I'm actually going to integrate over cases where tn plus 1, right, where t3 is actually greater than t2. And that doesn't sound good, because if I integrate h2 and t3, and if I integrate t3 greater than t2, then I'm integrating over extra stuff that I shouldn't do. So what procedure we actually do is, right, so now the problem, right, problem is I integrate over stuff I don't want to, right? Namely, I integrate over ht2. This is my integrand, right? This is my integrand. But because this is my integrand, right? And if I integrate it within, I want to integrate this integrand within, I want the triangle. But the triangle is hard to do. So I try the square. Right? I try to integrate over a square. But now I want to get rid of this extra triangle, right? And so the reason why I want to integrate over a square later is because then that will actually change our limits to be the same, and then that becomes a product, and then that's very convenient. Then that allows me to write something like d to the 2t, right? Where I just have a double integral, limits are the same, so 0 to t1. But at the problem at the current moment, I need to get rid of this. But it turns out that if I have it turns out that if I to get rid of this extra triangle, all that I actually need to do is I actually need to put a time ordering operator in here. If I put a time ordering operator in here, that orders the two, then in the case where I integrate over this triangle where t3 is greater than t2, right? This is something that I didn't like, but now integrating over this region where t3 is greater than t2 would be essentially integrating over the bottom triangle twice. So okay, so what is this time ordering operator? Is essentially saying t of this time ordering operator of these two operators is equals to h of t2, h of t3 if, okay, I'll just write it over here, h of t2, h of t3 time, okay, is this if t2 is greater than t3, and it's the other way, right? H of t3 if h of t2 if t3 is greater than t2, or if I flip the two around, then I'll just h of t3, sorry, h of t2 is less than t3. So this is a time ordering operator on the two. This is a time ordering on the two operators over here. So I wanted to get rid of this. I wanted to get rid, right, of this extra triangle. But if I integrate, if I change the integrand from just strictly this thing inside the bracket, right, h2, ht2, and ht3, if I change it into t of the time ordering of ht2 and ht3, then this triangle, essentially, right, this triangle will always be flipped around, because this triangle represents this case all the time. So this triangle, instead of getting rid of it, I actually have just duplicated. Actually, I just duplicated the top triangle. So this triangle becomes, right, this triangle becomes this under time ordering. This triangle becomes the following triangle under time ordering. And this triangle is something I've wanted to integrate over. So essentially, right, the upshot of all this is that integral of 0 to t1 of dt2, integral of 0 to t2 of dt3 of h of t2 and h of t3, right? This expression is actually equals to integral of 0 to t1, right, of dt2, integral of 0 to t1 this time, right? You notice the change in the limits of integration of t3. I now integrate over a square instead of a triangle, right, of time ordered of ht2 and ht3. So by adding this time thing, okay, I still need a factor of half over here because so essentially what this is saying, I need a factor of half. Essentially what this equation is saying is integral over the triangle of ht2 and ht3, right? This is bad because I want the limits of integration to be the same, right? So I wanted to duplicate it over into a square. But that wasn't too nice because if I just integrate the same thing, right, then I have some extra stuff I don't want to integrate over. But then it turns out that these two are actually equal, right? This is actually equal. Region 1 is equal to region 2, right? 1 is equal to 2 if I change the integrand from ht2 to ht2 to h3 t3 to, if I add in this time ordering operator, then I can integrate over the square, and taking the half, right, I get the same result because 1 is equal to 2. If I do it, this time ordering must be very important because if not, this time ordering, right, is responsible for the fact that 1 equals to 2, the two regions I integrate over. So I just wanted to hope that explains a bit of the step that I did over here. So for this one, right, is I integrate over a line. This one I integrate the second term, I integrate over a square, and then the third term, right, I integrate over a cube, and so on. And for each one of them, they'll pick up a factorial factor. They'll pick up a factor that attenuates it. So the first one will be 1, second one will be 1 over 2, the third one will be 1 over 3 factorial, right, representing how many ways there are to permute t2 and t3 and t4. Yeah. Okay, the time limits. Oh yeah, thanks for reminding the time limit. I will try to. Okay, so essentially now I've transformed all the time integrals, right, from 0 to some triangle in time. I've transformed it all into the same time, which is t1, right? I've transformed all of them into t1. Now you see on the right hand side is all t1, and that actually allows me to write the thing as a product now. And if I write it as a product, right, then it's a product of the same terms. Then I can write exponential, but I put a t in front of it, denoting that for basically this denotes that if I expand this in terms of if I expand this out in terms of Taylor expansion, right, all the operators, all the h, right, I must put a t in front of them, and that would collapse it down. So this is how we get the time evolution operator. By considering the Schrodinger picture, we get the time evolution operator in terms of time order exponential. And I will now open a new Zoom again. Yeah, sorry. Okay, see you guys in the new Zoom.